All right, as we are getting ready for Unit 10, let's review some important topics. All right, first of all, temperature. Important definition that you need to know. Temperature is a measure of the average kinetic energy of the particles in a substance. So as you can see, the particles right here on this side have less kinetic energy. The particles on this side have more kinetic energy. So these particles on this side right here would be moving faster, which means they would be at a higher temperature. So again, the definition of temperature is a measure of the average kinetic energy of the particles in a substance. All right, so the average kinetic energy of the particles in a sample of matter is expressed as, you got it, temperature. All right, so there are various types of energy: mechanical, thermal, nuclear, kinetic, potential, sonic, electromagnetic, chemical, lots of types of energy. What we need to remember for sure is the law of conservation of energy, which states that energy is always conserved, hence law of conservation of energy. What that means is energy is never, ever, 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 ever created or destroyed. Energy just changes form. It can go from chemical to mechanical, from potential to kinetic, but not from potential to poof, nothing, and not from nothing to poof, mechanical. Just changes form. Heat is the transfer of thermal energy from objects at a higher temperature to objects at a lower temperature. But not just any old objects. The objects have to be in contact. Air counts. So if the air is warmer or colder than the object, then there can be transfer between the object and the air. But in order for heat to transfer between two objects, they must be touching. And the heat will flow from the higher temperature object to the lower temperature object until there's an equilibrium. So the temperature is going to be somewhere in between. So whatever the warm object was, say 100, whatever the cold object was, say 20, the final temperature is going to be somewhere between 120. So here you can see the blocks are separated. There's not going to be transfer between the two blocks. They come in contact. The heat will be transferred from warmer to colder until there is an equilibrium reached and they are the same temperature. Which form of energy is transferred when an ice cube at 0 degrees Celsius is placed in a beaker of water at 50 degrees Celsius? Do you remember? Yeah, thermal. Okay, now comparing potential and kinetic energy. Potential energy is stored energy, whereas kinetic energy is the energy of motion. Remember, temperature is a measure of the average kinetic energy. So stored energy, potential, energy of motion, kinetic. Then we have entropy. Entropy is disorder or randomness. Okay? If particles are organized neatly, like look at this. Look at this neat organization. Look at this neat organization. That is low entropy. When we have higher randomness, higher disorder, we have higher entropy. Systems favor high entropy, randomness, or disorder. I like to think about it like student lockers or bedrooms. Tends to be disorder unless you do something about it. So systems favor high entropy and low energy. They always want to have less energy and more disorder. It's too much work to keep order. Systems favor high entropy. In terms of disorder and energy, systems in nature have a tendency to undergo changes toward, do you remember? Yeah, greater disorder, higher entropy, and lower energy. Entropy is a measure of, the disorder in a system, randomness, disorder. Which equation represents a change that results in an increase in disorder? So I'm getting more random. So think about it. When you have a solid, very ordered. Liquid, they can slide past each other, and a gas, the particles are far apart, moving all around. So if there's an increase in disorder, you're heading toward a gas state. All right, now bonds breaking versus bonds forming. breaking bonds, like in order to, if I just like grab this pencil right here and wanted to like snap it in half, I'd need to put some energy in to make that happen. So breaking bonds is endothermic. You have to put energy in. So the opposite is true of forming bonds. Energy is released, exothermic. Now in reactions, in reality, most of the time they're bonds breaking and bonds forming at the same time, most reactions. So it's a mix of things happening. But in general, the rule is breaking bonds, endothermic, forming bonds, exothermic. Okay, let's look at what is happening here. It says, given this equation, it's balanced. Which statement describes what occurs in this reaction? So let's look at it. We started with this, F2. That means two F's connected together. It would be F, F. On this side, we have the F's, the fluorines, but they're separated. They're no longer bonded. And then we see this. So this, it means energy is being put into the reaction, so energy is absorbed. So that means I know this is wrong. If energy were being released, it would be over here on this side of the equation, but it's not. So I know energy is being absorbed. Now it's happening to the bonds. Started like this and ended like this. So a bond is being broken. So energy is absorbed as a bond is broken. All right, exothermic versus endothermic. Remember, endothermic energy is absorbed, taken in. Exothermic energy is released, given off. All right, so look at this reaction. Which statement is true? So you can see this. I have endothermic, exothermic, and I have releases and absorbs. So here is what's going to give me the hint about this reaction. Look at where heat is. It's on the product side. So is that releasing or absorbing? Well, it's on this side. It's coming out at the end. It is releasing heat. So that means I know these two are wrong, all right, because they're definitely not absorbing. And what is a reaction called that releases heat? Well, it's exothermic. Products versus reactants. We say the arrow as yield. So this would be sodium plus chlorine yields sodium chloride. 2 water yields oxygen and 2 hydrogen. Spontaneous reactions. What does spontaneous mean? Well, it just happens on its own. And usually the rule for spontaneous is that means, remember, systems favor high entropy and low energy. So spontaneous reactions are ones that fit that narrative. They result in lower energy. That's exothermic. And they result in higher entropy, more gases. So if we look at reactions that tend to be spontaneous, they're going to fall into those categories. Exothermic, lower energy, and then they're going to be more gases being produced, which is going to increase the entropy. All right, so remember this table, it tells you heats of reaction and it indicates whether it is negative or positive. And remember right here at the bottom, the minus sign indicates exothermic reaction. So exothermic, exothermic, exothermic. Oh, wait, here's one. This one would be endothermic because it's positive. So if it's negative, it's exothermic. If it's positive, it's endothermic. And remember, exothermic tend to be spontaneous, endothermic, not spontaneous, which should make sense because if you have to add energy in, how is it spontaneous? Okay. All right, based on table I, which compound dissolves in water by an exothermic process? So I'm going to look at table I and look up each of these substances and look for the exothermic one, which means it has a negative sign. And there's going to be your answer. Which equation represents an exothermic reaction at 298 Kelvin? Again, what I'm doing is looking at table I, and I want to find each of those reactions, and I'm looking for the one that is exothermic, so it would be negative. And there we go. All right, are you ready? Let's get a taste of the new stuff. So a few new topics. All right, first of all, equilibrium. Equilibrium can only be found in reversible reactions. So if the reaction is only going in one direction, we can't have an equilibrium. In order to have an equilibrium, we've got to have a forward and a reverse reaction happening. And for equilibrium to occur, the rates of the forward and the rates of the reverse are going to be the exact same. They're going to be equal. So the forward reaction is happening and the reverse reaction is happening, but they're happening at the same rate. Equilibrium requires a closed system. So in this visual right here, without something at the top of this beaker, of this container, gases can escape, right? Gases can leave. They can escape this container. So we can't reach equilibrium. In this case, something is blocking the gas from escaping, so we can reach equilibrium. What is a catalyst? Well, a catalyst is a substance that speeds up a reaction. It provides an alternate pathway. It's going to lower activation energy. It's not used up. But here's the weird thing. It doesn't affect equilibrium. It just makes the reaction get to equilibrium faster. So it doesn't change only the forward. It doesn't change only the reverse. It makes the forward happen faster and the reverse happen faster. So the equilibrium happens faster, but still reaches the same exact equilibrium. All right, so you can see here's a reaction without a catalyst up here. Do you see how it requires more energy? With the catalyst down here, it requires less energy, but we have the same starting point, the same ending point. It just takes us less energy to get there. And then we have collision theory. Collision theory is that in order for a reaction to happen, particles have to collide. That makes sense, right? It can't be across the room from each other. So the particles actually do have to collide. But it's not just any old collision. The particles have to collide, yes, but they have to collide in the right way. So they have to be lined up correctly, and they have to hit with enough energy. So real soft collision, no reaction. Hard enough energy, okay? Also lined up right. So if they have to hit this way, but they hit this way by mistake, no reaction. So it has to be lined up correctly and enough energy. How much energy? Well, at least the activation energy, which we'll talk about. So that is just a taste of what we're going to learn about in this unit. With a lot of review, there's going to be a lot more to come. So I hope that you learned something new today.